In this video, we're going to go over the three basic types of rigid body transformations. So the translation, the reflection, and the rotation. Now, we talked about these types of transformations when we went through the textbook, but I wanted to go ahead and go through these again just to make sure you're clear on exactly what's happening with these transformations, in particular the rotation. I think the rotation can be the most confusing to understand. Okay, so what is a transformation in general? Not just a rigid body transformation, but any transformation. Well, all we're talking about there is that, so we can start with any figure, 2D or 3D figure, like shown here, okay? And you could be transformed from this starting state to another state. So we could start here, and then from there we could shift this anywhere in 3D space, rotate it, flip it, stretch it in certain directions, shrink it in other directions. Okay, and so when we study transformations, all we're trying to do is understand. So if this figure was transformed from state 1 to state 2, we're trying to understand all of the fundamental transformations that took place to go from this state to this state. Okay, now, but there's certain types of transformations that we call rigid body transformations. And these are the types of transformations that don't change the shape or the size of the figure. So there's no stretching or shrinking or scaling, right? Did I show scaling? So there's no scaling up or down or stretching, no change of shape or size. Okay, so if you think about it, based on all of the types of transformations I just showed, the ones that didn't change the shape or the size were the translations anywhere in 3D space. The rotations, this is just showing a rotation in the plane, but you could rotate it within the plane as well, right? Or the flipping. You could flip about, that was just flipped about like a vertical or a horizontal axis, but you could flip about any axis or any point or plane, right? And none of those transformations changed the shape or the size of the figure, which means that if all you've applied are rigid body transformations, then the transformed figure and the original figure are congruent, meaning that all of the corresponding sides and angles are still equal. And that's why it's important whenever you specify a transformation that you state. So you'd have these vertexes. Let's say you'd call this rectangular prism A, B, C, D, E, F, G, and that has been transformed into another rectangular prism with new letters. But you want to line up. You want to say that this rectangular prism A, B, C, D, E, F, G has been transformed to a new rectangular prism H, I, J, K, L, M, N, and you want to make sure that those that you line it up correctly. Like A corresponds to H, B corresponds to I. I lost track of where these went here, but if I was doing this more officially, then I'd want to keep track of which one of these vertices or matches up with the vertice on the transformed figure. It's really important. Okay, so now let's break down each one of these types of rigid body transformations to understand the fundamentals of what's happening. All right. First, let's start with a translation or a shift or a slide. Okay, all that's happening there is you're starting at this initial state, and it's strictly a shift anywhere in 3D space, anywhere. Okay, let's say here. That's it. The nature of what's happening here mathematically of what just happened is, so if we started with, we had rectangular prism A, B, C, D, E, F, G, H, and that was transformed to prism I, J, K, L, M N O P. So I got the corresponding points right. You can see. You could line up these points to know which point corresponds to which. What's happening, what just happened here is that, so with any kind of transformation, no matter what it is, rigid body or non-rigid body, you'll always be able to draw a vector that connects corresponding points. Always. For any kind of transformation. So we can let's do this for A to I, right? So we've got, let me make sure this is clear. We've got rectangular prism A, B, C, D, E, F, G, H was transformed to rectangular prism I, J, K, L, M, N, O, P. So let's draw the vector that shows where point A went after the transformation. So A went from here to here. Okay, and again, I want to make this clear that it doesn't matter what kind of transformation you have. If you think about it, you could do this. You could draw this kind of vector for any corresponding points for any kind of transformation, right? Now, but what's unique about a translation is that, so we get this vector here. This is going to have some direction in 3D space as well as some magnitude, right? Some total distance combined with a direction, right? Well, with a translation, all corresponding points, the vectors that connect all corresponding points are going to be exactly the same. So if we connect G to O, those 2 points are corresponding. This is going to be the exact same vector as the one connecting A to I. The exact same magnitude, the exact same direction. You could do this with any, it doesn't have to be the vertices, whatever, right? Here to here. Any corresponding points, it's going to be the exact same vector. That's the essence of what's mathematically happening with a translation of a figure. Okay, now let's talk about reflections. Okay, so in general 3D space, you can reflect about a line or an axis, you can reflect about a plane, or you can reflect about a point. And all this, when you do a reflection, all this means is that if you compare the figures before and after the transformation, they're going to be symmetric with respect to that line, that plane, or that point. And we talked about, in the textbook, we talked about exactly what symmetry about a line, a point, or a plane means. Okay, so if we reflect this here, let's see, I'll tell the software, the sketching software, to reflect this vertically, flip the layer vertically. So what it's doing is this entire layer here, there's like a horizontal line that, the line that splits this entire layer on the screen in half, and it flipped this about that line. Okay, so this was a flip about a horizontal line, so so we call that like a vertical reflection, right? If you flip about some line, then the resulting symmetry is in the direction perpendicular to that line. So this is a vertical symmetry here about a horizontal line. And so that's the idea, though. When the transformation we just applied was that we flipped this. We flipped this about this line. And what a flip or a reflection or a mirroring, you can use either one of those terms, it just means that if you compare the transformed, the untransformed and the transformed figure, both of those are going to be symmetric with respect to what you flipped about. Okay, and so we know what symmetry about a line means. It means that if you, so okay, let's put the corresponding points here. What we're going to have is, so F corresponds to N. This is going to be N. G corresponds to O. C corresponds to K. D corresponds to L. B to J. A to I. E to M, H to P. Okay, so what symmetry about a line means is that all points on the entire figure are going to have a corresponding point on the other side of the line of symmetry. No matter what point you pick in the original figure, it's going to have a corresponding point on the other figure on the opposite side of the line, which means that if 2 points are corresponding, then you can connect those 2 points and that line with a line, and that line is going to be bisected and perpendicular to the line of symmetry. So if we connect F to N, there you go, perpendicular bisector. It's 2 equal parts here, and it's perpendicular to the line. Same with G to O, and D to L, and A to I. See? All these lines are bisected by the line of symmetry, and they're perpendicular to the line of symmetry. And you could do this with any point, even in the middle of the box, wherever. There's going to be a corresponding point on the other side. Okay, but you can flip about any line anywhere in 3D space, right? We could flip about this line. It would just be the same idea. It would flip over here, and it'd be the exact same concept. All the corresponding points would be bisected by this line and perpendicular to this line. Okay, now, but what you can notice, though, is that when it comes to reflections, so we can go through the process of drawing the vectors that connect corresponding points. You can do this with any transformation. So, okay, there's the vector connecting F to N. All right, but now let's do another vector. Let's connect the corresponding points D and L. Well, look, those are different vectors, right? But this is different from the translation, where all of the vectors that connected corresponding points were exactly the same vectors. So that's a characteristic that's unique to translations. And you can just see that it's not that just because you have a rigid body transformation, that doesn't mean that all the vectors that connect the corresponding points are going to be exactly the same. That's just for the specific type of rigid body transformation, the translation. Okay, now, but you can also do reflections about planes or points. And this makes sense that you can do this based on what we understand the meaning of a reflection to be. It's that the before and after the reflection, if you compare the two figures, they're symmetrical with respect to that line or that plane or that point. And we know that you can have symmetry about a line or plane or a point. So if we were going to reflect about a plane, this could be any plane oriented in any way in 3D space. Okay, the idea is if you compare the figures before and after the reflection, the corresponding points are going to be symmetric with respect to the plane. And we know all this means is that those corresponding points, if you connect them, so I'm not sure what, I don't know if this is an accurate reflection about this plane here, but let's just say these were corresponding points. Okay, then this line here is going to be bisected by the plane, and it's going to be perpendicular to the plane. That's the idea. You could pick any point on the original figure, any point, anywhere, and it's going to have a corresponding point with respect to that plane that it was reflected about. Okay, now, but we could extend this to a reflection about a point as well. So we could reflect about this point, which, based on what we understand to be the meaning of point symmetry, what's going to happen is the transformed figure and the untransformed figure are going to be symmetric about this point. So we can think about in that case, then this would kind of flip to a certain extent to over here, and then all corresponding points would be symmetric about this point, which means they'll be equidistant from the point. So I probably drew this too far out, but all corresponding points are equidistant from the point. There's no perpendicularity when it comes to point symmetry. It's just that if this point would be point J, this point would correspond to point J, B and J correspond, these two lengths are going to be equal. And if So point D corresponds to point L. If you drew D through this point, it would be equidistant. This isn't an accurate reflection, but it would go, if you connected point D to point L, it would cross through the symmetry point, and then the symmetry point would bisect that line. And this would be true for all corresponding points. And so you could reflect about any point. Pick any point in 3D space, you can reflect about it, right? Okay, now, the last rigid body transformation is a rotation. We talked about in the textbook as how we interpret the meaning of a rotation is that, so you're going to be rotating about some point, any point in 3D space, and the angle of rotation of corresponding points about that point of rotation are all going to be exactly the same. So let's say we applied a pure rotation of this figure about this point. So maybe something like that. Okay, what this means is that, so we can see that this is, here are the corresponding points, I, J, K, L, M, N, O, P. What this means is that if we look at the angular rotation that point A went through to get to its point I here, so we would do that by, we would connect a line going from the point of rotation to each of the 2 points. And so these 2 lines here form a plane, right? And so we can think about there's going to be some angle here. Well, if you do this exact same process for any corresponding point, so let's see, F corresponds to N. And then you measure that angle, it's going to be the exact same angle as N to I. Now, but the plane that contains the line segments connecting the point of rotation to N and to F could be different. It's not like these are all going to be in the same plane. I mean, they won't in a lot of cases, because especially if you have a 3D figure like this. So the plane that contains these angles is in general is going to be different. But regardless of that, still the angles of rotation are going to be exactly the same for all points, right? We have L to D, or your point D went to point L. That's going to be, it's getting hard to see, point L to point D to point L, that's going to be the exact same angle, theta. And you could do this for any point, not just the vertices. You could do this for any point anywhere within the figure, as long as the 2 points are corresponding from the untransformed to the transformed, angle theta. And once again, you can see that with a rigid body transformation, with any reflection, translation, rotation, the 2 figures are congruent before and after. Okay, now just note, though, that it is the case that there's different ways you can rotate about this point. Here, maybe we rotate more up and towards the back. Up and, we're kind of going in this direction and around the back, or maybe we could have come more forward in this direction and up over the point. Okay, but no matter how you do it, the fundamentals of the relative angle between untransformed and transformed corresponding points being exactly the same applies for any way you rotate it about the point. Okay, and also note you could put the point at the center of the box. In that case, it would just be kind of rotating in place. But even in that case, there's an infinite number of ways you can rotate it. You could rotate it like this, right? But whatever the rotation that you apply, once you apply that rotation, if you're studying the specifics of that rotation, then all of the before and after angle change between straight lines that connect corresponding points on the untransformed and transformed figure, it's all going to be that same exact angle.